All right, so we had just looked at graphs of tangent and cotangent function, I believe is where we stopped. All right, so now let's get into graphs of the reciprocal functions. So of course, when you're talking about reciprocal functions, we are talking about cosecant and secant. We've already looked at cotangent for the tangent function. So as you can see here, when we're talking about cosecant, we're basically talking about 1 over sine as our function, and for secant, of course, would be 1 over cosine. So remember, the idea here is, since we define these functions as reciprocal, anytime your sine of x value is going to be 0, what are we going to see for the cosecant function when my sine function is 0? Vertical asymptotes, right? Just like we saw with the tangent and cotangent function. In that same way, whenever your cosine of x value is going to be 0, your secant function is going to have vertical asymptotes at that point. So if you look at a cosine function for values of pi halves, right? And then you can look at rotations of that. So at pi halves, 3 pi halves, 5 pi halves, all of those, we are going to have 0 for our cosine function, which means at those same places, our secant function is going to have vertical asymptotes. And if you look at the definition on the next page for the secant function, and it kind of, they're comparing this with the tangent and cotangent function, because those are the same places where your cotangent and tangent functions would also have vertical asymptote. So for sine, remember sine is 0 at the starting point, right, at 0, and then pi, and then 2 pi, 3 pi. So basically, in rotations of pi, you are going to have vertical asymptotes on the cosecant function. So if you can remember, at x equals n times pi, for the sine function, we will have zeros, which will lead to vertical asymptotes. In that same way, when x is pi halves plus n pi, your secant function is going to have vertical asymptotes. And you can kind of see what these graphs actually end up looking like on this page here. So they're basically saying the way we go about graphing these functions is you actually start with the original sine or cosine function. That's that little light colored gray graph you are seeing on those graphing images here. And then the idea is, at places where you have your x-intercepts on the sine or the cosine function, you will notice that's where we are doing the vertical asymptotes for our reciprocal function, right, for both of these. And then at places where you have a hill on the sine or cosine function, since we're doing reciprocal, right, we're going to invert that and make it into a valley, but it's going to be bounded by these vertical asymptotes. So it's actually just going to be this little portion right here, right? You're not going to see that curve that you see in the sine and cosine function. So every time you have a hill, it's going to become a valley in the reciprocal function. And every time you have a valley, it's going to become a hill in your secant or cosecant function. And then again, you can see right here for our cosecant function, sine has 2 pi period, so that will also be 2 pi for the cosecant. Your domain in this case, of course, is all real numbers except all those places where you're going to see the vertical asymptotes at, so that's n pi. Range, and of course, this is using the idea of just sine of x, right, and cosecant of x. Now, if you add your amplitudes, phase shift, and that kind of thing, the answers will change. But for just a basic cosecant function, your range is going from -infinity to -1, and then it starts at +1 to +infinity. Obviously, vertical asymptotes at the same place where the domain is undefined. For a cosecant function, you have no intercept. So it's not going to cross the x-axis. It's not going to cross the y-axis, because at the y-axis, this guy actually has a vertical asymptote, right? So it's not going to cross at that point. And then, of course, sine is an odd function, so cosecant is also an odd function, which means symmetry about the origin. For your secant function, Same thing, cosine has a period of 2 pi, so secant also has a period of 2 pi. Now, at places where cosine is undefined, we have vertical asymptotes for the secant, so that's going to be at pi halves n plus pi. And then again, same values for your range. You're going from negative infinity to negative 1, and then positive 1 to infinity. Now, this guy will actually have a y-intercept, which is going to be at this point 0, 1. And again, if you did phase shift, then that value can change. And remember, cosine is an even function, so secant is also an even function. And we talked about that last time. Tangent, cotangent, sine, cosecant are odd functions. Cosine and secant are even functions. And I've already talked about the hills and the valleys, so you can kind of read this paragraph if you like. And they're just kind of highlighting that fact that where you have a relative, maximum on the sine function, you're going to have the relative minimum on your cosecant function. Okay, so let's take a look at how we can graph these reciprocal functions. So here you're looking at the function y equals 2 times cosecant of x plus pi over 4. Again, that 2 at the beginning is telling us our amplitude is 2. We know by default cosecant has a period of 2 pi, so that means you take your value in the parentheses x plus pi over 4 and set it equal to 0 for 1 and set it equal to 2 pi, the period of the function. And you're basically trying to figure out what your interval is going to be, right? So you're going to get x equals negative pi fourths from here and x equals 7 pi fourths from that 2 pi equation. And then, the idea is you are still trying to graph the original function first, which means the sine function. And then based on that, we'll reverse and do our cosine function. So basically, go ahead and find your places where you have the x-intercept, which would be the same place where you have the vertical asymptotes for this function. And you can see that in this graph here at negative pi over 4, at positive 3 pi over 4, 7 pi over 4. And then you can obviously keep repeating that. You're going to have your vertical asymptotes. Go ahead and graph with your amplitude of being 2 units, and then reflect that with the cosecant function. So let's take a look at our example here, and we'll try to see how we can come up with all of these values to help us out. Alrighty, so we have y equals 2 times cosecant of x plus pi halves. So to help us out, we will start by graphing y equals 2 times, the cosecant would be sine, right? The reciprocal function. X plus pi over 2. Okay, so in this case, we know your amplitude is going to be 2. Period. What do you think the period for this function will be? Yeah, because your b value is 1, right? The coefficient of x. So that's going to be 2 pi over b, which will be 2 pi over 1. So it's 2 pi, which means for our equations, we're going to take the value in the parentheses, x plus pi halves, set it equal to 0, and x plus pi halves equal to 2 pi. Okay. And then get your x value from there. And what do you get for your x? Uh-huh. Negative pi over 2, very good. And what's 2 pi minus pi halves? Yeah, 3 pi over 2, very good. Okay, so if we're thinking about this in terms of our sine function, let's see what those key points would look like. That function was 2 times sine of x plus pi halves. You're starting out at negative pi halves. What should our next x value be? Because we're going from negative pi halves to 3 pi halves. Cool. And then the last one here would be 3 pi halves. What's halfway between negative pi halves and 3 pi halves? Pi halves, yeah, it'll be positive pi halves. Because that distance is going to basically be pi halves and plus 3 pi halves, right? Okay, what is halfway between negative pi halves and positive pi halves? Zero, yeah. And halfway between pi halves and 3 pi halves? Pi. Right, very good. Okay, so if I put negative pi halves in here for my x value, what do I get for my function value here? So if this is negative pi halves plus pi halves, what will this guy become?
Zero.
Yeah, 0, because they cancel each other out. And what is sine of 0? Because that's the starting point on your unit circle, right? So what is sine of 0? Let's go sine. Because what's that ordered pair at 0?
1, 0.
1, 0. So remember, the first coordinate is cosine, the second coordinate is sine. So your sine is going to be 0, which means 2 times 0 will give you 0. So basically, that's 2 times sine of negative pi halves plus pi halves. You're doing the same thing for all the other x values. And what will we get for when x is 0? So 0 plus pi halves will be pi halves, right? And pi halves is what angle? 90 degrees. So what's the ordered pair at that point? 0, 1. So what is sine? 1. Yeah, so it would be 2 times 1, which is 2. And again, you know, anytime, if it helps, draw a unit circle so that you know what points you're looking at. So this guy here was 1, 0. This guy here is 0, 1. So at pi halves as your x value, what are you going to get? What is pi halves plus pi halves? Pi. So that would be which angle? 180, which is here. And what's this ordered pair? Okay, so what's our sine value again? 0. Now, obviously, remember you have that repeating pattern. So technically, this guy would be our intercept, right? This first point that we did. If he's the intercept, what is this point? The maximum. You're back at the intercept here. So what should this point be? -2. Very good, which would be your minimum, right? And then where are we at for 3 pi over 2? You're back at the intercept, yeah, which means you'll be at 0 again. So use that repeating pattern to your advantage also, since we know how these functions work. All right, so let's take a look at our graph for this guy. Okay, let me set this guy down. We are doing a longer x-axis. And we have an amplitude of 2. And then we are going from negative pi, 0, positive pi halves, pi, 3 pi, 2 pi. And if we need to do 2 full periods, let's see how far we need to go. Is at negative pi halves, we are at 0. At 0, we are at 2. And then positive pi halves, we are back to a 0. Pi was negative 2. And then back to a 0, right? Bless you. And this is our sine function that we're doing right now. So that's one period, right? So if I wanted to extend this guy, my next point on the right will be a maximum and then an intercept. So I can go ahead and extend this. Bring it down. If I go to the left-hand side, since I'm at an intercept, which means my next point should be a minimum, which would be right here, and then I'd be back at an intercept. So this would be our 2 full periods. And in red, we have the y equals 2 times sine of x plus pi halves. Okay. Now at every position where you have the x-intercept is where you're going to have your vertical asymptotes. So then we need to start drawing our vertical asymptotes at all of those x-intercept places. Okay. All right, so now how are you going to draw the reciprocal cosecant? What did we look at in that example?
Where there's the maximum, so it's going to be
not really parabolas. I'd probably just call them relative minimums is what the official term is. But yeah, you're just doing the valleys, right, where the hills are.
Mm-hmm.
So that means if we start from the leftmost part here, you're actually going to have this guy go down, but remember it's going to be bounded by those vertical asymptotes. And then where you have the hill here at positive 2, you're going to have a valley for the hill, a hill for the valley, and one more. And then in the green, we have our original function that we have to graph, which is the cosecant of x plus pi halves. And that's kind of one of the things I like about graphing these reciprocal functions is because, well, you're getting extra practice to do the sine and cosine, but that's where the majority of your work is. And we've already done that in the previous section. So that means you're literally just drawing the guideline by using the sine or cosine function and then just inverting the hills and the valleys to get your cosecant
So the
secant.
actual
Is the one in green.
The actual curve on my road, which is going to be like isn't going to be touching those hills.
Yeah, they do touch at these
But
points.
the actual curve doesn't really matter. As long as it's touching it.
Well, you do want to keep it within your between the vertical asymptotes, right? So the idea is, because remember how asymptotes work, the idea is this line would start getting closer to the asymptote, but it would never touch it or cross it. So you want to make sure you're getting closer to your vertical asymptote. Don't make them too narrow. So remember, the red is the guideline, the graph in green is the actual graph that we're looking for. Any other questions? So Adrian, does that make sense?
Yeah.
Yeah, awesome.
And the negative would just look everything. Like if it was -2 cosecant.
Yeah, then you would see the reciprocal. Yeah. I mean, sorry, the reflection. Yeah. Very good. Alrighty. So that would be our graph for y equals 2 times cosecant of x plus pi. All right, let's look at a secant one here. So this example is looking at y equals just 2 times x. So obviously amplitude is 1. B value is going to be 2. So if B is 2, what will that make of our period? If B value is 2. Yeah, so if cosine usually has a period of 2 pi, which means secant will also have a period of 2 pi. If B is 2, your period will just be pi. So you can see how narrow these graphs are, right, compared to the other example we just did. And then, you know, of course, once you figure that out, then you can use your key points to find out where your x-intercepts are going to be. Where you have x-intercepts, again, you're going to have vertical asymptotes for the secant function. And then using the same idea of a cosine as your guideline graph, you will then come up with the secant curve. So we're kind of doing something similar to that with y equals secant of x over 2. So let's go ahead and see what our values are going to be here. Okay, so y equals secant of x over 2. So what's our amplitude here? Amplitude is 1. Very good. We are going to be graphing cosine of x over 2. Period is going to be what? No, because you're dividing by 1/2, right? Yeah, very good. It will be 4 pi. Alrighty, very nice. Okay, and then what are we going to do next? What did we do for the previous example? So in our case, what is the bx minus c here? Yeah. Start by 0 and this is where we do our little equations. And since your period is 4 pi for this guy, your next one would be set equal to 4 pi. So what's your x value from that first equation? Yeah. And from the second one, 8 pi, yeah. Because your b value changed the period of the function, right? So you have to see specifically for this function what the period is and then set it accordingly. Okay, good question. Alrighty, so that gives us 8 pi, which means our interval for this function is now going from 0 to 8 pi. Are we okay so far? Okay, so again, like we did before, let's find our key points, and we're doing this for cosine of x over 2. starting at 0 and finishing at 8 pi. What would be our halfway point here? 4 pi. And then the first halfway point between 0 and 4 pi? 2 pi. And for the last one? 6 pi. Very good. So if I have cosine of 0 over 2, which is basically cosine of 0, again, like I said, you can always use a unit circle to help you out. Cosine of 0 is the starting point here. So what is that ordered pair? 1, 0. So what's our cosine value then? Very good. If I use cosine of 2 pi over 2, that becomes cosine of pi. And what's the ordered pair at cosine of pi?
-1, 0.
Yeah, because pi is at 180, right? So -1 is the value here. Okay, so you can repeat that process for the other numbers. And what will we get for x equals 4 pi? Yeah, you're back at the starting point, aren't you? 6 pi? -1. And 8 pi. Okay, so do you know what's happening here?
It's just a
Pattern of what points? Maximum, minimum. So what are we missing in here? Yeah, intercepts are in between, and I kind of wish now I had left space, but you know I'm going to use color. So if you wanted to find the intercept between 0 and 2 pi, where would that be at? Pi, which would be at 0, right? And then where would my next intercept fall? 3 pi. Okay. The next one, 5 pi, and 7 pi, yeah. So that may be something you want to make sure you include because we need that alternating pattern. Okay, so we're now ready to do our little graph here.
That's so long as you do the calculations for sums and just follow the
No, that is just so if you were looking at your notes, you should know how we came up with those values. But yeah, I mean, alternating pattern is how I go about because you know, since this is coming from a cosine function, you know we start at a maximum, intercept, minimum, right? If it's a sine, you start at the intercept and then you go maximum, intercept, minimum, right? Yeah, so I would, if the pattern is easier, I would go with the pattern, yeah. Alrighty, so we started at maximum, intercept, minimum, and then repeating that. Okay, so we're going in pi. That's 1 pi, 2 pi, 3 pi, 4 pi, 5, 6, 7, 8. And remember, we need 2 full periods to come out of this. And our period is 4 pi, right? So we should be getting 2 full periods from this. All right. So we are starting at 0, 1. At pi, you have 0. At 2 pi, we have -1. 0 again. +1, 0, -1, 0, and +1. Okay, let's try this again. Okay, so that would be our cosine function in red. So that's y equals cosine of x over 2. Now what should we do? Where should we start so that we can draw the secant function? Yeah, very good. Through the intercepts, you want to draw your asymptotes. So the first one in this will be at pi, and then at 3 pi, 5 pi, and 7 pi. Okay, very good. And then you're just changing the hills and valleys, right? Okay, so on this first part between 0 and pi, since we are seeing just a part of that maximum, so that means this will be just a part of this minimum here. And then we've got a valley, which will then become a hill for the secant function. Whoa. And you know, the best you can do with those curves, they're not going to come out looking perfect. Now again, here at the 8th pi, you're doing a partial valley. And then again, in green is our original function, which is the secant of x over 2. And then you can see based on the amplitude, the range of your function is going to change, right? So it's not going to be default. Now, of course, in this, we are still starting at +1 to infinity, and we're coming from -infinity to -1. But in that previous example, since we did have an amplitude change, your range would then be going from -infinity to -2, and then starting at 2 to infinity. So just kind of keep that in mind. That amplitude does make a difference on the range of these functions, right? Okay, any questions on both of these graphs?
So these are really
So domain would be all real numbers except all those values where you're seeing your vertical asymptotes or intercepts for the sine or cosine. So you can, since they wanted us to do 2 full periods, we actually kind of stayed on the right-hand side, but you can repeat this pattern on the left. So let's say if you did go left, we would be at -pi, -2 pi. Yeah, and you're basically just mimicking that same pattern, right? All right, so if I have a asymptote at pi, where would my asymptote start at on the left-hand side? Yeah, you will be at -pi. And then the next one? -3 pi, very good. And then it should be -5 pi after that, right? So that would be -5 pi, and if you went all the way, it would be -7 pi. And then you're just repeating that pattern. So this guy would then complete and come down here. -1 here. And then you'd basically again end up at part of that maximum there, right? And then when you're doing your reciprocal function, then this guy we would need to complete our little valley here. This would become a hill. This would be your valley. Hill here, and then just part of the valley here, right?
You want us to label the curves too, like you did? Like,
The original function?
that you want us to label them, like you want us to label them?
Yeah, because it's a good practice. So that way, you know, if somebody's looking at your graph, they know that this is the original graph. So yeah, you can just put it next to the graph, or you can do it, but you're coloring it in different colors. Yeah. So this one, of course, would be 4 full periods, right, instead of 2 full periods. But usually the standard is to give 2 full periods. And so it can be straddling the y-axis. You can do half on the negative side, half on the positive side. In this case, just because our values came out to be from 0 to 8 pi, we just kind of stayed on the positive side. But yeah, like I said, you're just mimicking that shape on the negative side. All righty, very good. Now this last part on section 1.6, we want to talk about the damped trigonometric graphs. And what that actually means is that you are multiplying your trigonometric function with a damping factor. So you can see the first example we're looking at here is the x times sine of x. So in this case, to try and figure out what our graph would look like, we actually use the absolute value properties, but we also use the idea that we know a sine function only goes from +1 to -1 because that's its range value. So we're actually using that to help us out here. And so the idea is if my original function is x times sine of x, we know the value of sine of x will stay anywhere between basically -1 to +1. And so keeping that sign aside, your value of the function actually can then go from 0 to absolute value of x. So you know how we set up absolute value functions, if you remember this from college algebra, we always take the absolute value and set it equal to a positive number first, and then for the other part, we say, okay, it can also be negative, because with absolute value, the idea is what's the distance from 0, right? You can have that same distance on the positive side or negative side. So we're actually using that property right here when we say negative absolute value of x is less than equal to x times sine of x less than equal to absolute value of x. And this actually helps us decide between what values our function is going to stay. So that actually means your your function value of x times sine x is actually always going to stay between -x and +x. And how that helps us, especially when we're trying to graph this, you will notice we actually graph these positive x and -x lines as our barrier lines, basically, because your function, as you can see, will stay between those lines. It doesn't go beyond that, because this damping factor of x that we have being multiplied with sine of x is actually restricting how far your function can go. So it's going to stay between these lines of +x and -x. And then, of course, we know that sine of x is going to be 0 at pi halves and values of, multiples of pi halves. So that's actually what they're saying. At those values, you are going to have, no, wait, hold on. No, sine is 0 at multiples of pi, because you add 0, pi, 2 pi, 3 pi is where sine is 0, and then sine of x is +1 or -1 at pi halves and multiples of pi halves. So that's what they're actually using here to try and see. So basically what's going to happen is at all the values where sine should be +1 or -1, you're actually going to be touching the lines for positive and -x. So all of these points where my graph is touching the diagonals x and -x is where we have multiples of pi halves. At all the places where my sine function is crossing the x-axis, that's going to be the places where your sine function is going to be 0 at, so multiples of pi. And that's basically how we come up with this graph of a damped trigonometric function. So the example that we are looking at is being damped, or the damping factor is actually your x squared function here. So we are taking x squared times sine of 3x. So that means that your value of sine of 3x is actually going to be between the -x squared and +x squared. So those would be your parabolas, right? Opening up and down. So instead of having those straight lines with y equals x and y equals -x, we're actually going to be looking at curves between -x squared and +x squared. And since instead of this guy being a sine of 3x function, sine of x function, this is sine of 3x. You see how this guy changed here? When you had sine of x, our value of 1 was going to be at pi halves plus n pi, right? But now that you have sine of 3x, basically it's that same value being divided by 3 because you're solving for x in that case. So you actually take pi halves plus n pi and divide both of those by 3. And that's how you get this value of pi over 6 plus n pi over 3. And then, of course, instead of your zeros being at n pi, they will now be at n pi divided by 3. But again, the same idea is at multiples of pi over 6, your graph is going to be touching those curves for your parabola. And then at multiples of n pi over 3, you're going to be at the x-intercept on your damping graphs. So it's a pretty interesting way of looking at, what happens when you bring this other variable in and how that changes, because normally your sine has that even shape. It just stays in that little frequency model that it has, but now bringing in those values of x or x squared is completely distorting basically the shape of your function over here. So we're actually going to do something similar to this example we just saw, and we're looking at x squared sine of 4x. So in this case, so we have x squared sine of 4x. So one of the things we have to keep in mind is that x squared being a square value, right, is always going to be a positive value, because no matter what you put in for x squared is always going to come out being positive. So x squared is going to always be greater than 0 for any real number x. And we know that sine of 4x is also going to stay between -1 and +1 value, because remember, it's the amplitude that changes the range, right? Not the 4x part of it. So we know it's the range is still going to stay between +1 and -1. So using that and the absolute value property, we can also actually make the argument that this guy will also stay between a -x squared and +x squared. So basically, this is going to be sandwiched between our x squared and -x squared curves. Now, I wanted to show you that calculation of how do you figure out where your sine values are going to be 1 and where they're going to be 0. So in this case, if you look at, and let's do that a little bit separately from here. So you are given sine of 4x, and we know sine of 4x can give us a value somewhere between +1 and -1. Just for a sine function, where do you have the 1 values at? What theta values do we get 1 at for sine? So again, you can think of a unit circle. Where do we get sine as 1? Pi over half. And then the next one would be 3 pi halves. And it would keep going in that order, right? Okay. So for this function, sine of 4x, it's going to basically end up becoming, and it keeps moving in n pi's, right? Because it's going to be at that 180-degree angle that it keeps doing. So this is what I was talking about. To come up with those values, you're basically dividing everything by 4 to figure out what your equations are going to be for these guys. So you go from pi halves divided by 4, which will become pi eighths, and n pi divided by 4 as the cycle. Okay, in that same way, you can think about where are we going to have zeros at. So zeros for a sine function happen at what values? Right, very good. Pi, 2 pi, and that order, right? So that means for 4x, it's going to be pi, and then multiples of pi. So if you divide these guys by 4, which actually, if you think about it, pi over 4, if my n is 1, is also going to be pi over 4, right? So you can actually just write this guy as n pi over 4. Because if n was 0, this thing would disappear and you would have just pi over 4, right? But if n was 1, then you're automatically getting a pi over 4. So this actually becomes redundant if you leave it that way. So it just cleans up into n pi over 4. All right, now here comes the interesting part. And this is very, very interesting when you try to graph this. And I have not been very successful at making it look neat and clean. Okay, so remember these curves are going to be sandwiched between our x square and negative x square values. And we're going in increments of pi over 4. So that's going to be positive pi fourths, pi halves, 3 pi over 4, and then pi, 5 pi over 4. What would that be? 2 pi. Okay. So pi fourths, pi halves, 3 pi fourths, and pi. And I'm doing this really very rough sketch here. Because your pi divided by 4 is approximately 0.78, right? Pi halves is going to be what? 1 point something, because it's going to be half of 3.14, right? So your pi halves is going to come out to be 1.5. Now we know for an x square function, your ordered pairs can be 0, 0, right? 1, 1, 2, and 4. So you're going to have to now figure out on the x-axis where that 1 is going to fall, and then you can try and get the 1, 1. So again, your pi halves is about 1.6. Pi fourths is about 0.7 or 0.78, 0.8. So you're basically looking at halfway between this is where you're going to have your 1 value, right? And so you're going to have to do 1 and 1. Let me see if I can get it. No. Okay, so if you're doing 1, 1, that's going to be about somewhere in there. Negative 1 would be again halfway between negative pi fourths and negative pi halves. So your -1, 1 would be somewhere over there. So the idea is, where would 2 fall? About halfway between pi halves and 3 pi over 4. So that would be then at 2, 4, which would be somewhere over here. -2, 4 would be somewhere over there. So something like that. And this is obviously freehand, so you know it's not going to be very accurate. This is y equals positive x squared. And then you're going to mimic that for the negative side. So between these guys halfway is -1 here, -1 here, and then negative. So I don't know, somewhere down there. And this is your y equals negative x squared, so something like that. Now, for our x squared times sine of 4x function, your x-intercepts, and that's this value that we calculated, is going to be at multiples of n pi over 4, right? So where would my first x-intercept be on the right-hand side? Pi over 4. So that would be right at this point. And then which one would be my next x-intercept? Yeah, pi over 2. And then 3 pi over 4. So at all of those markers that we just drew, right? It's going to have x-intercept. So same thing is going to happen on the left-hand side. Now, at pi 8, and then with multiples of n pi over 4, it's going to be touching these curves of the x squared and negative x squared. So we know pi 8 is basically the halfway point between all of these, right? So the idea is halfway between here, you're going to have your graph touching on the, and of course you would be starting at maximum, minimum, maximum, minimum. So this would actually be, and you would actually also have an x-intercept at the origin also, because if n was 0, your x-intercept would be there. So if we are starting with the origin as our starting point, then halfway between this, I should have a maximum point right here between 0 and pi over 4. So between 0 and pi over 4, I will have a maximum. Then between pi over 4 and positive pi over 2, I will be at a minimum. So that means my graph is coming down this way. Then between pi over 2 and 3 pi over 4, I will be, oh boy, at a maximum. And that's, yeah, these graphs do not come out looking pretty. And then I'm just stopping right there because I think we've made enough mess on our course as it is, but it's actually going to end up looking something like this. And then, you know, of course, doing that on the left-hand side. So since we started with the maximum, on the left-hand side, between 0 and negative pi over 4, you will be at a minimum. So this guy will be going down here. Then between negative pi halves and negative pi fourths, you're at a maximum. And then between negative 3 pi over 4 and negative pi halves, we are at a minimum. No. Okay. Yeah, they don't. I mean, this is probably one of those examples where a graphing calculator or a computer program makes more sense than doing it by hand. Because, you know, we cannot expand these out further than what we are able to draw. And I don't even know where this halfway point is anymore. He's going to be somewhere, I don't know, somewhere over there.
So is the one that 3 pi over 4 the minimum value, the one that follows it? Is that a negative, or is that just an estimate?
Which one?
On the right side, it follows like 3 pi over 4. The one that follows it, the minimum. Is that a negative, or is that just an approximation?
You know, I think it should be at -4, but again, with this freehand, without a grid, it's kind of hard to say, because it looks like almost we should be at +4 at this point, and we should be -4. So the best way to know that would be to take the, what would this be in pi8s? Because this would be 7 pi8s. Yeah, so I would take 7 pi over 8, put it into our function, and then see what y value you get.
Okay.
Because I think that would be the best way to do that. So if you did x squared, so x squared here would be 7 pi over 8 squared multiplied by sine of 7 pi over 8. It's actually giving 2.89. So just a little under. So yeah, as I told you, these graphs are just so terrible to draw. And I'm still kind of not sure how I want to draw this last part, because, you know, my curve is going to be so much higher. It almost looks like this guy would be going up, right? And we still haven't hit the curve. So your curve is going to be somewhere over here that it would be hitting it and then coming back down. So yeah. These ones are very, very tricky to draw. And then again, in red is our actual function. Again, the x squared minus x squared are those kind of like the asymptotes, but not really, because, you know, obviously they're blocking your graph from going up, but you can still have values at those places. So a very, very interesting looking function. But what I really want you to understand is, you know, in examples, you're not just going to be seeing functions that are just plain sine, cosine, tangent, cotangent, secant, cosecant, right? A lot of times that damping factor is going to be part of some of these examples you do, so at least we should have an idea of what those functions would look like and how they restrict the workings of the trigonometric function. I mean, just by multiplying x or x squared in your function, you can see how it changes your y values, your graph, extensively. Alrighty, so I think that was the last thing we have to talk about. And then, of course, on the next page, you will see the little summary for all the different functions we have looked at. So again, remember, your sine function always starts at the intercept and then goes to a maximum, intercept, minimum, intercept, whereas a cosine function will always start at a maximum, and then it will go from maximum to intercept to minimum to intercept. Those are the only two functions where you don't have to worry about vertical asymptotes, right? Because those are the only two functions where your domain is all real numbers. But as soon as we get into tangent and the reciprocal functions, of course, with the tangent and cotangent, we have, you know, our function which still has all real numbers for the range, but, you know, of course, your domain is going to be broken up by those vertical asymptotes, and then you can see what our cosecant and secant functions look like. And of course, you know, they haven't done the little guidelines of the original functions in here, so you've just got your secant and cosecant functions in there. So what I would recommend you guys to do is definitely practice with those 6 main functions, but I would also try practicing with the damping factor, just so you know how to be able to at least come up with a basic shape of a graph. I mean, obviously, you know, we didn't do a great job graphing this, and I'll admit it, because it's really hard. And even the first time I taught this class, I must have practiced examples like 5 or 6 times, and then I just gave up because I was like, with freehand, there's just no way to make it look pretty, make it look nice, right? So even if you give me something close enough where we can see where it's crossing the x-axis at, where it's supposed to touch those other 2 graphs at, you are good to go. I'm not looking for perfection. I'm just looking for making sure you're at the right points you're hitting your graph at, okay? All right, and that's about it for 1.6. So any questions on this last example? Are we good to go? Yeah? You think you're ready to take a quiz on this for next class?